Okay, let's go ahead and get started. So I hope everyone had did you forget your? I hope everyone had a nice weekend. So last time we talked about Lagrange's theorem, which tells you that the size of a subgroup divides the size of your group, and it also tells you the number of left cosets of that subgroup inside of your group. So today we're going to see two more corollaries of Lagrange's theorem. So for the first one, I'm going to have you fill in the blank of what this is saying. So the statement of this is that groups of prime order are, and then you will fill in the blank. So I'll give you a few minutes to think about what this statement should say and what its proof is, and your hint is that this is a corollary of Lagrange's theorem. Bean. Okay, let's see what this statement should say. So let's let A be an element of G. Then what are the possibilities for the order of A? Yeah. Yeah, so this is either the order of G or 1, because the order of A has to divide the order of the group, and the group we've assumed has prime order, so the only divisors are 1 or the order of the group. And then the only element that has order 1 is the identity, so any non-identity element is then forced to have order G. So if A is not equal to the identity, then the order of A is equal to the order of G. And that means that the subgroup generated by A is equal to the entire group G. So G is cyclic. Okay, and then that, so this sort of classifies groups of prime order, because we also know that cyclic groups are always isomorphic to Z mod the order, so that means that whenever you're handed a group of prime order, you know automatically that it's like Z mod P. Okay, are there any questions about this? Yeah.
Why does the last implication follow?
Okay, so the order of A is equal to the order of the subgroup generated by A. So that means that all of the elements of G are accounted for by just powers of A.
Oh, so like closure is everything.
Yeah. Other questions? Okay, so for the rest of the time, we're going to build up towards a second application of Lagrange's theorem. And this is about something called group actions. And this appears like, so this idea of group actions this appears all across mathematics and probably physics and other sciences as well. So this is just like a really important and pervasive idea in like the way that mathematicians view really like any type of mathematical object. So let's see what this is all about. So I'll give you a definition. So let's let G be a group, any group, not necessarily finite, and we'll let X be a set. Then a group action is an operation for multiplying any element of G and any element of X to get another element of X. And it is going to have to satisfy some properties. So let's say we have a little g that came from the group G, and we want to know what does this do to X. It's going to give me some other X prime in X. And it has to satisfy first the identity times any element of X. That has to be just that original element, so the identity doesn't do anything. And then second, we're going to ask for associativity. So if I do H times an X and then multiply that again by G, that has to be the same thing as first multiplying G times H within the group G and then multiplying that element on X. And in this case, you would write, or sometimes you'll see G and then this like curly arrow X, and that's you would just pronounce this GX on X. Okay, so you just have like some notion of what it means to have a group element operate on elements of the set X. One thing that I want to note, the map, so if I take any little g and g and I make a map from X to X that's given by just left multiplication by g, is a permutation on X. Okay, so let's see some examples of group actions, just to get an idea of what types of things we're talking about. So the first one is called the trivial action. So what does the trivial action do? Given any group G and any set X, if we do G times X is equal to X, this is a group action called the trivial action. Okay, let's see another, a less trivial one. So 2, for any group G, if we set X to be equal to G, then G acts on itself by left multiplication. So we would define G times an X to be equal to Gx, where on the right it's understood that the operation is the one from the group G. And this was sort of what we saw when we looked at the proof of Cayley's theorem. This was like what we were doing. We were viewing the group as acting on itself and looking at what permutation does the element G correspond to. Okay, maybe a less, a more familiar one. How about? So the general linear group, which I'll remind you what this is because we haven't really dealt with this at all. So this is n by n invertible matrices over a field K. So if you like, you could take K to be the complex numbers or the real numbers. So GLN K acts on the vector space K to the n by matrix multiplication. Right, so we have a way of taking elements of this group, which are matrices, and we know how to multiply that on a vector of length n, and that gives you a group operation of GLN on the vector space K to the n. The last one, which is the example that I'm going to focus on later in the lecture. This is like a more geometric example. So the group of rotations of the cube. So you can imagine if I took a cube and my group is ways that I can rotate so that I get back a cube again. This acts on the set of faces of the cube. So maybe I can draw an example. So if we have a cube, I'll draw the edges that we can't see in like this lighter color. Okay, so say this is the cube, and I'm gonna label the faces as well. So 1, 2, 3, those are like the front faces that we can see, and then maybe behind it are 4, 5, and 6. Okay, so one way that we could rotate this would be to spin it around this line going through the middle of it, say rotate it by pi over 4. So what that would do is it would bring the face labeled 3 to where the face labeled 2 is. It would put 2 where 5 is, and it would put 5 where 4 is, etc. And it would fix 1 and 6. So let's say this is our group element G. So this is rotation on like z-axis clockwise by pi over 4. So what this does is G times the set of faces. So for example, let's say G times 2. G would take the face 2 to the face 3. And so on. And G would fix the face 1. Etc. Does it make sense? Okay, are there any questions about group actions or like the setup or anything like that? Yeah.
If you scroll up, I have a question about the associativity.
About which one?
Associativity.
Yeah.
Is H in the definition a member of the group or the set?
Yeah, so in this would be, sorry, I wasn't as clear about this as I should have been. So little g and little h are elements of the group, and then little x is an element of the set big X. So this over here, like these multiplications are the group action. This multiplication is the group action, but this multiplication is the multiplication in G. Yeah. Are there other questions? Okay, so along with this, I'm going to introduce two sets. First, the first one will be called the stabilizer of an element, and the second one is the orbit of an element. So to be a definition. So let's let G be a group acting on a set X. Then for each, and I'm going to call the elements of X Y because I feel like it can be hard to differentiate between little x and big X. So for each Y in X, we'll let stab G of X. So this is going to be equal to the elements G in G such that G times X, or sorry, I said that I was going to do Y and then I started writing with X's again. So stab G of Y is going to be those elements of G that fix Y or stabilize Y. So this is, I would call this the elements that stabilize Y. And we call this the stabilizer of Y. Yeah, question?
I'm saying that the element Y is the stabilizer, or that the list is the stabilizer?
This list, stab
Okay.
GY is the stabilizer. Yeah. Yeah.
So this is for a specific group action, or is there only one group action to do that?
So we've fixed a particular group action. There could be multiples, right? Like G could act trivially on X, or it could act in some interesting way. So we've picked a particular group action, and now we're going to look at the stabilizer. Yeah. And it'll be clear from context, like what the group action is. Usually typically you wouldn't have like multiple different actions floating around. Yeah, okay, so other questions about the stabilizer? Okay, so a proposition about the stabilizer. This is a subgroup of G, so stab G, Y is a subgroup of G. So why is this true? We have like a couple of things that we have to check. So we need to show that the identity is in the stabilizer. We need to show that if two elements are in the stabilizer, then their product is in it. And we need inverses as well, because we didn't assume that this was finite. So okay, so why is the identity in there? Yeah.
Because under group actions, the identity will not by Y actions.
Yeah, so when we defined what a group action was, we asked that the identity always fixed every element. So this means that the identity will be in any stabilizer. Okay, good. So what if A and B are in the stabilizer? Why is their product in it? Yeah.
So you have A times X equals X, and then B times X equals X, and then you would set AB times yeah, set AB times X.
Yeah, so we had like associativity, right? So we could like reassociate this. And then Bx is X, so we're left with Ax, and this is X. Yeah. Okay, maybe I need more room for this last one. Okay, why do we have inverses? Yeah.
If A is in the stabilizer, then A times Y, or A applied to Y equals Y. Then you can multiply it on the left by A inverse, and by associativity, the left-hand side becomes Y, and the right-hand side becomes A inverse Y.
Yeah, so we could reassociate this. And then this is just the identity times Y, which is Y. Okay, good. So the stabilizer is a subgroup. Are there questions? Okay, so now I'm gonna introduce another set, and this is called the orbit. So this is another definition. So we're gonna let G be a group acting on a set X. And then for any Y in X, we'll let orb sub G of Y be the set of all GYs such that G is in G. Okay, so this is like a subset of X. It's all of those elements of X that you can act on Y and get to one of those elements. So it's called the orbit of Y. Okay, so let's do an example just so you can get a handle on what the orbits and the stabilizers look like. So let's let X be the set of elements 1, 2, 3, 4, and 5. And I'm going to let G be the following group. So it will contain the identity. It will contain, and this is, I'm going to give this to you in terms of permutations. So it's going to contain the permutation 1, 2, and it's going to contain the permutation 3, 4, 5. And then it's also just going to contain everything else that follows from it containing those two elements. So we also have to have 3, 4, 5 squared, which is 3, 5, 4. And then we need the product of 1, 2, and 3, 4, 5. And then we also need the product of 1, 2, and 3, 5, 4. And that should be all of the elements. Okay, so the main thing is it contains this, and then everything that you get out of multiplying those two things together. And, of course, the identity. Okay, so I'm going to give you a few minutes to compute orbits and stabilizers of the elements of X. And you can feel free to discuss together, and then we'll talk about it after you've thought about it for a few minutes. Okay, so let's go through a couple of these examples. So, for instance, let's do the stabilizer of 1. So this is asking which elements of G do not move 1 at all, right? So we just have to look at which of these permutations do not involve 1. So this would be the identity 3, 4, 5, and 3, 5, 4. Okay, so that's the stabilizer of 1. We could ask also, what is the orbit of 1? So which elements of X can we send 1 to? Well, it looks like really the only options are we could fix 1, so 1 can go to itself, or 1 can go to 2. And otherwise, if you're 3, 4, or 5, there's no way to send 1 to 3, 1 to 4, or 1 to 5, so this would be the orbit of 1. Let's do another one maybe. So let's do the stabilizer of 4. So these are the elements of G that leave 4 fixed. So that would just be the identity and the transposition 1, 2. And then if we wanted to compute the orbit of 4, we could leave 4 fixed. But there's also permutations that send 4 to 5 and 4 to 3. Okay, but there's no way to get from 4 to 1 or 4 to 2. Okay, so these are a couple of examples. I'm not going to do every single one, but from this, you might notice the following pattern, which will be the next theorem, which is that the size of the orbit times the size of the stabilizer is the size of the entire group G. So we'll let G be, and I guess we should assume these are finite, so let G be a finite group acting on a finite set X. Then the order of G is equal to the order of the orbit of an element of X. So let's call this Y. Times the size of the stabilizer of Y, where Y is an element of X. So this is super useful, and we'll see an example where we're able to compute the size of a group, which is at first non-obvious, but the orbits and the stabilizers are themselves very easy to compute. But in addition to that, like, this theorem pops up all over the place. So for example, like I've used this theorem in my research like multiple times over the course of the last year. It just like, it comes up all over the place, and it's just like useful for translating statements about orbits or about stabilizers into statements about the size of a group. And often, like, when you see this in applications, this equation will be rearranged. So you might, for example, know something like, you might already know the order of the group, and you might know the size of the stabilizers, but you want to know the orbits or something like that. Okay, so let's see how to prove this, and this is a corollary of Lagrange's theorem. So we know that the stabilizer is a subgroup. So by Lagrange's theorem, the quantity G divided by stab Y. This is the number of left cosets of stab Y in G. Okay, so what we're going to do is establish a correspondence or a bijection between the left cosets of stab Y and elements of orb Y. Okay, so if we manage to do that, then that tells me that the number of left cosets, which is this, is equal to the number of elements in the orbit. So giving me this correspondence, so if I give this correspondence, then that proves the theorem. Okay, so I'm going to give you the correspondence. So I'm going to define T, which will be a map from left cosets of stab Y to orb Y by, so it's going to send a so we'll have a coset of the form G times stab Y, and this gets sent to GY. Okay, so if I have a coset, we know that that was obtained by multiplying by some element of the group G. So let's say it looks like G times stab Y. Then I'm going to send that to G times Y, which is an element in the orbit of Y. Okay, so the first thing that we need to check is that this is well defined. And what I mean by that is that I could have two different ways of representing one coset, right? I could have written it as G times stab Y, but there may be another H such that this is equal to H times stab Y. So let's suppose this is the case. Then we need to show that GY is equal to HY, right? So that would mean that I defined this map in a way that makes sense. Okay, so if G times stab Y is equal to H times stab Y, then G inverse times H is an element of stab of Y. I think this was one of the properties of cosets that we proved, I think last lecture. So properties of cosets. So if you have two cosets that are equal, that means that we can take G inverse H, and we know that that is in the coset. So, in the subgroup. So that means that G inverse H times Y is equal to Y. And in other words, that means that hy is equal to gy as desired. Okay, so we showed that the map we defined makes sense. So now we just need to show that it's injective and surjective. So let's start with injective. So suppose gx, or sorry, I'm doing y. Suppose gy is equal to hy. Then that means that g inverse hy is equal to y. So g inverse h is in the stabilizer of y. So again, just reversing the properties of cosets that we just did, that means that g times stabilizer y is equal to h times the stabilizer of y. And so that means that the function is injective, because we showed that if the two outputs are equal, then that meant that the two inputs had to have been equal. Okay, and then for surjective, if gx is an element of the orbit of x, then if I apply my map to if I apply my map to g times, oops, and I wrote x again instead of y. So if gy is an element of the orbit of y, then t of g times the stabilizer of y is going to be equal to gy. Okay, so given any possible element of orb y, I know which element maps to it, so that means that my function was surjective. And that concludes the proof. So I think the meat of this argument is accomplished in showing that your function is well defined, and also in applying Lagrange's theorem. Like Lagrange's theorem is doing the heavy lifting here. Okay, are there questions about this? Yeah.
I was wondering how g inverse times h is in staff y tells us that g times staff y. Or no, below that. Like the other way around.
Yeah, this one?
Yeah, I was wondering how like g inverse on the next line. Yeah, that tells us the next thing.
So this was the same like property of cosets as for here. So I think we had a property that said like, yeah. Other questions? Okay, I have an example, which we may not finish before time is over. So going back to, so let's let G be rotations of a cube. And then I'm going to let X be the faces of the cube. So let's compute the order of G using the orbit stabilizer theorem. So the order of G will be equal to the size of the orbit of a face times the stabilizer of a face. Okay, so let's take our cube. And let's say this face that I've labeled with a star is the face that we've selected. Okay, so what is the orbit of star? If I pick this cube up and rotate it and put it back down, what faces can star be? Yeah. Yeah, so I could pick this up and rotate it so that star becomes any of the other faces. So the size of the orbit is equal to the number of faces, which is 6. And then what about the stabilizer of the face? Which rotations of the cube leave that face fixed? Yeah, so okay, I heard some people say it. So if I like poke the face here and then rotate the cube around this, that will leave the star fixed in place. And there's 4 ways to do that. So that means that the order of G is equal to 6 times 4, which is 24. And if you wanted to compute this in different ways, you could think about like doing this in terms of the edges. So you could think of X is the edges of the cube or the vertices of the cube, and do a similar computation where you see what is the orbit of edges and what is the stabilizer of an edge and things like that. Okay, so I will see you on Wednesday, where we're gonna finally talk about direct products of groups, and then looking forward. Oh my goodness. On Friday, we're going to talk about something called normal subgroups. Bien. Wow. Bark bean. Do you have a question?
Yes. So this person has a dog. The deal he made with you. I know the deal he made with you. Her dog. Stop it. This is such a messy mess. I should go. Hey.
Have a good one.
Have a good day.